Welcome to our first lesson of Physics 20. So we're going to talk about vectors, free body diagrams, and physics principle 0. So this you've done before in Science 10. Scalar quantities referred to just magnitude, meaning how much. So an example of something that would be just a magnitude would be mass. Mass is a scalar quantity, right? Because you can say that you're 10 kilograms, but you wouldn't say 10 kilograms to the left, right? It doesn't have that direction, it just has that magnitude. Another example is time, right? So time you could say 2 hours, but you wouldn't say 2 hours up. That doesn't make any sense. Okay. So other examples include energy. You either have energy or you don't. You have 10 joules or you don't have 10 joules. Another example is distance. We'll talk about that a little bit more in detail, but you can go 2 meters. Yes, you can go 2 meters to the left, but we have a different name for that. Okay, so those are just examples of scalar quantities. So here's a little video we can watch that talks about the other type of quantity.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh! Ah! Gosh, it's so difficult sometimes to get the ball back inside.
So vector quantities, just like in the video, give both magnitude and direction. So examples of this are velocity. So I can move 20 meters per second. Sorry, it does that little skip. I don't know how to prevent that because I've switched my mouse and it still does it. So my velocity is 20 meters per second, but if I add a direction to it, right, then it becomes a vector quantity. So 20 meters per second to the left. Displacement is a vector quantity of distance, and I can go 2 meters, but I can go 2 meters up. I add that direction to it and it becomes a vector quantity. Okay, so some words are used to describe scalar quantities. So speed is just how fast you're going. Distance is just how far you go. Some words are used to describe vector quantities. So if I want speed but with a direction, it's velocity, 10 meters per second east. Right? If I want a distance but with a direction, I call that displacement. And sometimes we only want distance and sometimes we want displacement, right? If you're going for a jog, you wouldn't say, oh, I ran 5 kilometers north. Who cares about the north? You just want to know you ran 5 kilometers. But if you're trying to find directions to someone's house, oh, go down that road 5 kilometers to the north. Yeah, that's a lot more important. So some quantities don't have different words for scalar and vector. So acceleration, sometimes we want the scalar quantity of the acceleration. Sometimes we want to know, what's your acceleration? Is it 8 meters per second squared? Cool. But sometimes we want that direction as well. So acceleration doesn't have 2 separate words. But what we say if we're looking for the scalar quantity is I would ask, what is the magnitude of the acceleration? If I just add for the magnitude of the acceleration, then I'm just looking for the number. I'm looking for the scalar quantity. If I ask for the acceleration, then I'm looking for the vector quantity. Position is another term that comes up, which to describe an object's displacement from a reference point, which is usually a starting position, right? So we can see that we have this tree here as our reference position, and I would say that this kid is 7, these are meters, so 7 meters away from the tree. So does that make it a vector quantity or a scalar quantity? Well, I'm still giving a direction, right? It's 7 meters away from the tree, so it's a vector quantity. So position and displacement are the same thing. So when I talk about position on tests, just treat it like displacement. Yeah, it's the same thing, really. So there's different ways that we can express direction. So a very common one is north, east, south, and west. So with our compass, usually we have north, east, south, and west, like that. And because it works out like this grid, this graph as well, usually north and east are positive, usually, and south and west are negative. But as long as we make one of them positive and one of them negative, it doesn't really matter. But this is usually our convention that north and east are positive. Okay, forwards and backwards. So I can go forwards, I can go backwards, and usually forwards is positive, backwards is negative. Usually, it doesn't matter though. And then up and down. So again, up is usually positive, down is negative, but there's lots of situations that'll come up that will actually make these opposite. So we'll talk about that a little bit more in detail when we do questions like that. So the term net is used to describe the total you get when all the positives and negatives are factored in. So somewhere where you might see net in everyday life is your net pay. You have gross pay. Your gross pay is just, you make $12 an hour, you work 20 hours, that's your gross pay. So your gross pay is your total amount that you make, but then you have deductions, right? This is American, so these are different things, but we have CPP, we have EI, so you subtract all these deductions from here for a total of $20.35. So this is your positive money, and then you factor in your negative money, and what you end up getting is you get your net pay. So net just factors in all the positives and negatives. So Larry's cat travels 10 meters forward, turns around, then travels 8 meters backwards. What is the total distance traveled by Larry's cat? So if I'm doing this question, right, and I'm looking for distance, well, I don't care about direction. Larry's cat travels 10 meters forward, then Larry's cat travels 8 meters backwards, but he goes 10 meters and 8 meters for a total of 18 meters. That's it. That's all I need. But if I look at this in terms of displacement, what is the net displacement of Larry's cat? Well, displacement, I care about those positives and negatives. So I'm going to make forwards positive, backwards negative. So instead of saying 10 meters, I'm going to say positive 10 meters, because positive means forwards. And then Larry's cat goes 8 meters backwards. I still add them, but I'm going to add negative 8 because it's backwards. So positive 10 plus negative 8 is going to equal positive 2 meters. And we have to indicate what this positive means, right? We made positive forwards, negative backwards, so we have to have a direction after our magnitude. So we end up getting 2 meters forwards as the answer. If you didn't put that forwards in there, it wouldn't be correct. Okay, so this is a board question. So pause the video, try it on your own, and see if you get the right answer, and I'll go through it right now. So 6 people pull on a tug-of-war rope. Team Red has Eric, Mike, and Josh, who pull with 12, 19, and 21 newtons all south. Team Blue has Matt, Doug, and Sean. They pull all north, 19, 12, and 26. If we want to find the net force on the rope, so this N is newtons, just in case you don't remember that from past classes. So all that we have to do is add those up. So I'm going to make south negative, and I'm going to make north positive. So the first team pulls to the south, so I'm just going to go negative 12 newtons plus negative 19 newtons plus negative 21 newtons. So those are the 3 that pulled to the south. And then I'm going to add the team that pulls to the north. Let's put these in brackets here. So the first one is positive 12 newtons. and positive 19 newtons, and positive 26 newtons. Okay, so you can add this all up in your calculator, but if we have negative 12 and positive 12, they'll cancel out. Negative 19 and positive 19 will cancel out. So we just have these two remaining. So what we can do is we can go negative 21 plus 26. We don't put positives in our calculator. And we end up getting positive 5 as our answer. So this would be positive 5 newtons. And because force is a vector, we have to indicate direction. So the positive means that we're going north. We wouldn't want to say forwards for this one because we want to stick with the convention in the question. So it would be positive 5 newtons north. So net forces cause objects to accelerate. Now, acceleration is really confusing. So to start physics, we want to keep things easy by analyzing objects that are stopped or moving at a constant speed, right? We just do this to keep this easy to start things off. So what we need is we need Newton's first law. So Newton's first law says objects at rest will stay at rest, right? If you put your pen on your desk, it's going to stay there. That's pretty obvious. The second one seems obvious, but it's not as obvious as you think. Objects in motion will continue to move in a straight path at a constant speed until a net force acts on it. So I have a little GIF here, right? So the friction on this grass is really low. So what's happening with this dog is it's going at constant speed, but there's no net force acting on it other than the small amount of friction. So the dog just continues in a straight path, keeps going. Right? And if there was no friction on that grass, say that dog was in outer space or something like that, that dog would just slide forever and ever and ever and ever and ever. Okay, that's what Newton's first law says. Okay, objects at rest stay at rest, objects in motion continue in a straight path at a constant speed until a net force acts on the object. So to talk about forces, what we need is free body diagrams. So a free body diagram shows a diagram of all the forces of interest acting on the object. So all forces must be drawn going away from the object as pulls. Even if they're pushes, we draw them as pulls. And sometimes we only include the forces in the direction of movement. So I say sometimes because you'll get the idea once we do a few questions of when we do this. So how to draw a free body diagram. Start by drawing a simple shape, such as a square or a circle, without any surrounding objects. Sometimes we do draw the floor, just to show that it is on the floor. Use arrows always leading away from your object to represent the forces acting on it, and label your arrows with names and numbers if possible. The length of the arrow represents the magnitude of the force. So this is a little example. So they've drawn on these 4 forces acting on it. You can see that this force applied is bigger than this force of friction. So this is a bigger force than this one. It looks like these two are the same, so they're drawn as the same size. So we're not going to use these conventions, so I'm going to talk about what conventions we will use for our naming of forces. So these are the only ones that we're going to use in Physics 20. So yeah. So force due to gravity is Fg, and it's a force of attraction between two masses, so you and the Earth. That's force of gravity. Force applied we call Fa, and the force applied is just a general cover-all thing, so it can be applied by a person, a machine, an animal, colliding objects. Springs and ropes can also apply a force. There's frictional force, which always opposes your motion. Force of tension, which is the same thing as force applied, but only as a rope. The main difference between force applied and force of tension is ropes can only pull, you can't push, but force applied you can push or pull. Force normal, and this is the force exerted by a table or a surface. So to have a force normal, you need support by a table or a surface. The ground works, anything. And spring force is a force of compression or extension on a spring, and we're going to talk about that in a future unit. So mostly what we're sticking with is just these ones to start. So what we write is we write an FNet equation. So remember that net just means adding things up with all the positives and negatives included. So an FNet equation always follows a free body diagram. An FNet equation shows all the forces acting on an object added together with proper plus minus vectors. Okay, so this is our free body diagram, right? They called it force push, because you can call it anything you want, but we're just going to keep our conventions the same. So we have force applied, force normal, force friction, force of gravity. So when writing an FNet equation, the mistake that people make when they start off is they sort of combine them all. So we have these forces, which are in the x component, and then we have these forces, which are in the y component. It's important that we keep these separate when doing them. We wouldn't want to include all of our free body diagrams, or all our forces together in one equation, right? So this is our FNet equation for our x. We have our force of push and our force of friction, and then they do a separate one for, oops, I should say the y, which has force normal and force of gravity. We want to keep those separate, and we'll sort of combine them together later when things get a little bit more difficult. So let's do some examples. So to do these examples, we're going to use our friend here, which is our legless dog. And our legless dog is really nice because he doesn't go anywhere, and the only way that he can move is by us applying some forces to him. Okay, so we're going to draw a free body diagram and write an FNet equation for the following situations. A legless dog sleeping on the ground. Okay, so I'm going to switch my screens, and we're going to draw free body diagrams for the legless dog sleeping on the ground. So I'll draw the ground. This is a legless dog, and I can draw the forces acting on it. So if you're on the earth, you'll always experience a force of gravity, right? And if you're on a surface like the ground or a table or anything like that, you experience a force normal. So because this dog is not moving, it's just stationary, what that means is that my force of gravity is going to be the same size as my force normal. So now that I've done that, I can write an FNet equation. So I'm going to make up positive and down negative. So I write FNet is equal to my positive force normal plus my negative force of gravity. Now, think about this. What is our FNet in this? Right? When I add this plus this, what am I going to get? Well, I'm going to get 0. Right? So if I have 0 equals force normal plus minus, so I can just write minus force of gravity like that. Same idea. And I rearrange this equation, so I move force of gravity to the other side by adding a force of gravity to each side. What I end up getting is force of gravity is equal to force normal. Oops, that's a little bit off the screen. Force of gravity is equal to force normal. And that's what I'll always get when my FNet is 0. If my FNet is 0, these two forces have to cancel out, so they're always going to equal each other. Okay. So here's our next situation. A legless dog is being pulled at a constant velocity to the right because the brakes were left on. So my legless dog is being pulled at a constant velocity to the right because the brakes were left on. Cool. So let's do that one. So I'm going to draw wheels on my dog because we're moving now. So the dog is moving to the right, so most likely I have a force applied to the right. So in the question, it said a legless dog is being pulled at a constant velocity. So if I'm being pulled at a constant velocity, there's obviously force of friction going over here. Is that force of friction going to be smaller? Is it going to be same size? Or is it going to be bigger than my force applied? Think about it. What do you think? So a lot of people answer that it's got to be just a little bit smaller, right? If I want to move, it's got to be a little bit smaller. And that's actually incorrect. And that's a very common misconception in physics. If I go back to this, objects at rest will stay at rest, and objects in motion will continue to move in a straight line at a constant speed until a net force acts on it, right? So what a net force does is a net force causes objects to accelerate. If I'm moving at a constant speed, it means I'm not accelerating. And everything that we're doing is at a constant speed to start. We don't talk about any acceleration. So if I'm not accelerating, I don't have any net force, which means when I draw my free body diagram for this question, it's got to be the same size. So when I end up doing my, maybe it's a little bit bigger. There we go. Now they're the same size. When I end up doing my FNet equation, right, this is positive, this is negative. Well, FNet is equal to force applied. And instead of saying plus negative, I'm just going to say minus force of friction. To save a little bit of time, this is 0. What I end up getting is force applied is equal to force of friction. And that's what I get whenever I'm moving at a constant speed or whenever I'm stopped. I end up getting that they're equal to each other. So you'll notice in this free body diagram that I didn't include force of gravity, force normal. Are they there? Yes, they're there. Can I draw them in? Yes, I can draw them in. But we're focused on the dog is moving to the right, right? When we're talking about moving left or right, we don't necessarily need these in our free body diagram every time. We know they're there. We know they cancel out just like in the last question, but we're focused on the direction of the motion. So if you put them in, you're right. If you don't put them in, sure, you're also right. It doesn't make that big of a difference right now. Okay, and then I have one more. Someone is pushing down on the legless dog while he's not moving, and the legless dog loves it. This isn't animal abuse. So if I draw my free body diagram, so the legless dog isn't moving. So here's my legless dog, obviously out of the contraption again. We're not moving left or right, so we're more focused on force of gravity and force normal. The legless dog experiences a force of gravity, and it said that someone is pushing down with a force applied. So now what we need to ask ourselves, how big am I going to draw this force normal arrow? Am I going to draw it equal to my force of gravity last time, but there's more forces acting on it? How does that work, right? Well, think of these as negative, right? I have this arrow and I have this arrow. If I add those two arrows together, like that, so this is my force of gravity, this is my force applied. Well, I want my net force to be 0 because I don't want my my dog to be moving. It says the dog isn't moving at all. If I draw my force normal the same size as my force of gravity, well, I still have a net force. My net force is going to be this. That's what's going to be left over. So what that means is I need to make my force normal bigger than my force of gravity in this situation because it has to account for both of these. So I'm going to make it bigger. I'm going to make a really big force normal, and it goes off the screen there. That's how big it is. So when we write our FNet equation, right, I'll say up is positive, down is negative. So we have this positive force normal, and instead of saying plus negative, I'll just go minus force of gravity, minus force applied, like this. Well, again, our FNet is 0. My dog isn't moving. We add these to each side, so plus force of gravity plus force applied. And what we end up getting is force of gravity plus force applied is equal to force normal. Well, that's exactly what we said. These two going down must equal this one going up. So this is what we get with our FNet equation. Sorry, that's in the way there. So normally I would ask, is there any questions? But you can't answer that because you're watching a video. So hopefully that makes some sense. Hopefully. So this, why do I have naked people on this slide? So this just shows Newton's first law. So Newton's first law says that an object in motion will stay in motion unless a net force is acting on it. So Pioneer and Voyager were space probes that astronauts set into space to analyze Jupiter, Saturn, Uranus, Neptune, Yeah, in the 70s is when they sent them in. So they knew that they would send, this is it, I think this is Pioneer, one of the two. They look pretty similar. So they knew they sent Pioneer out to these planets, but they only gave it enough fuel to sort of analyze these planets. They didn't give it enough fuel to come home, and there's nothing on it. There's no people or animals or anything on it, so they knew that it wasn't going to go home. So when it was done its mission, when it was past these planets, what they did is they gave it one last little rocket boost, and then no more fuel is left. So what's happening is this ship is just moving, right? It's got a speed, and because in space there's nothing, it's just going to continue on forever and ever and ever at a constant speed because there's no net force acting on it. So knowing that it was going to continue off into space forever and ever and ever, they wanted to put a little information card on it in case some alien life forms ever found it. So they couldn't just put like English words on it because, well, the aliens wouldn't understand English, and there's also other languages in the world, so why would you choose English? So what they did is they used pictures. So this is the sun, this is Mercury, Venus, Earth. So they wanted to know that, yes, the space probe came from the third planet from the sun. And then this is a relative distance to other stars. So this is our star right here, and these are relative distances to other stars around, so they can, obviously if they find this, they're capable of space travel, so they're very smart, so they could figure out, well, what has these relative distances to a star, and they can find our star, find our planet, and then if they land on Earth, they can be like, well, they could land in a field and the field's full of cows and be like, hello, we found your space probe, and then the cows don't see anything, so this is what we look like. We'd be greeting them fully naked, pretty muscular as well, and this is how big we are compared to our space probe, which they would find. And this has to do with water. Hydrogen is a plentiful element here on Earth, so we know about that. But yeah, that's all the information that they sent out, so hopefully it's not evil aliens that want to take over the world and destroy us. This here is what they sent on, one of these is Pioneer, one of these is Voyager, I forget which one. So they sent out a different space probe, and they wanted a different sort of thing on it. So they sent out a gold record, and the reason that they chose gold, because gold won't break down in space, and gold will last forever. So this is a gold record. They have like this sort of space map information here. But on this record, they have sounds from Earth, so they have music. They have music from all sorts of countries. They have sounds of animals, sound of whales, sounds of big cities, so that if these aliens found this, they could hear the sounds of Earth and see what it was like. So they also included like a record needle and a pin, so that they can use it and they can hear the sounds. Also encoded in here are pictures. So you can encode pictures on a record, and if they were able to decode it, they'd be able to see pictures of Earth as well. Remember that this was in the 70s, so that's why they didn't have compact discs, they didn't have CDs, so this was all done on a record. So you can search up gold space record or something like that if you want to know more information about it. It's really cool. So let's do a board question. So try it out on your own, and I will go through it and see if you can get the right answer. There are two applied forces acting on an object. The object is stationary. Only one applied force is 5 newtons to the left, and we want it to be stationary. So we're going to draw a free body diagram, write an FNet equation, and find the magnitude of the second applied force. So here's our object. Yes, there may be force of gravity, force normal. It doesn't really matter because they're talking about there's two applied forces on this question. So two things are pulling on this one object. So we have one applied force. We'll call it force applied 1. And it's 15 newtons to the left. So it said that the object is stationary. So if the object is stationary, well, there has to be an equal and opposite force applied to the right, which must also equal 15 newtons. So if I wrote an FNet equation, I would say that force applied 1, I'll say this is positive, this is negative, minus force applied 2. I know my FNet is 0 because it's stationary. I move this to the other side, I end up getting force applied 1 is equal to force applied 2. So 15 newtons must equal 15 newtons, just in opposite directions. So that's what I'm looking for that. We found the other force, we wrote the FNet equation, and we drew our free body diagram. If you put gravity in normal, it's fine. It's not wrong or anything like that. So let's try another one. There are two applied forces acting on this object and an object moving to the left at a constant velocity, and force 1 is 5 newtons to the right. So same things to do. Okay, so make sure you try this on your own before I go through it. We have an object and it says that it's 5 newtons to the right is force applied 1. So it says that it's moving at a constant speed to the left. So if we're moving at a constant speed, it means that our FNet is equal to 0 again, right? And our FNet is equal to 0. The only way to make it 0 is if I make force applied 2 5 newtons, right? If I make it 5.1 newtons, well, we don't have an FNet as 0. And if we don't have an FNet as 0, we can't move at a constant speed. So they have to be the same. So my other force must be 5 newtons to the left if my first one is 5 newtons to the right. And again, we get this. And we get 5 newtons is equal to 5 newtons. Hey, everything is going to be moving at a constant speed or stopped. Everything, FNets have to equal 0 for these first few lessons. These are physics principles, and they're in your data book. So these are physics principles that we'll be using. So right now, we're talking about uniform motion, so that's physics principle 0. So you can find that on the back of your data booklet right there. So these numbers are important on that because sometimes I'll ask you questions on tests about what physics principle you're using, and we're using physics principle 0 right now, where your FNet is equal to 0, and uniform motion means either it's stopped or it's moving at a constant speed. So physics principle 0 is used anytime you have a net force of 0. So when you have a net force of 0, you can use the following formula. V equals d over t. So I usually write it like this. This is change, which means d2 minus d1 over t2 minus t1. But the reason I don't usually include those is because, well, what's your distance 1? 0. Something minus 0 is just d2, right? Your time is usually 0 to start, so you don't include that, right? So v can be speed or velocity, and we can be in meters per second or kilometers an hour. Distance or displacement in kilometers or meters, and time in seconds or hours. Just if we're in meters per second, these have to be in meters and seconds. Just like if we're in kilometers an hour, this has to be in kilometers or hours. So there's another formula that's kind of the same. It's not on your formula sheet because it's still v equals d over t, but some questions will ask for average speed. And when it asks for average speed, you need to take your total distance over your total time. So what that's saying is, like, so if I'm driving somewhere, if I drive by my house, I might drive this distance, and I drive that through a school zone, which is 30 kilometers per hour, and then I leave the school zone, I drive a different distance, which is 50 kilometers per hour, and then I drive on the white mud a certain distance, which is 80 kilometers an hour. So I need to find my average speed by taking the total distance that I traveled during this time and divided by my total time that I traveled. Okay, average velocity is the same thing. It's just displacement instead of distance, so that means that direction makes a difference. So let's do a few questions. So Piper stole Annika's pencil, and Annika is chasing after her at a speed of 45 kilometers an hour. Annika was running for 14 seconds before she caught up with Piper. What was her distance traveled in this time? So because I'm just given a speed, I'm given a time, this is just a really simple v equals d over t style question, and that's how I'm going to do it. So I can use v equals d over t. I am trying to find what was the distance traveled, so I can rearrange it. T equals d over v, or sorry, d equals tv, and I can plug in my stuff, but my time is in seconds. So if I do 14 seconds, so if I try to plug in my speed in kilometers an hour and seconds don't go together. So what I have to do is I have to switch this into meters per second, because it says it wants the answer in meters in the question. So kilometers into meters, there's 1,000 meters in 1 kilometer. And then hours into seconds, there are 3,600 seconds in 1 hour. So if I type this into my calculator, 45 times 1,000 divided by 3,600, I end up getting 12.5. So that's 12.5 meters per second. And you can see that the seconds on the bottom cancels out with the seconds on top. So we end up getting meters as our answer. So if I just take my 12.5, multiply it by 14, I get 175. But in the question, there's only 2 sig digs, so 1.8 times 10 to the 2 meters would be a better answer. And it's asking for a distance, so we don't need any direction in there. So this question is different. So on a fishing trip, you paddle your canoe north at 2 kilometers an hour for 30 minutes. After realizing that you passed your fishing spot, you turn south and travel 1.5 kilometers an hour for 10 minutes. Determine your average speed for the trip and your velocity for the trip. So it's asking for our average speed, and it mentions two different trips in it, 2 different vectors. So let's draw this on. So let's draw out what's happening. So the first part of the trip, you travel north, and you travel at a speed of 2 kilometers per hour, and you do it for a time of 30 minutes. And then you travel south at a speed of 1.5 kilometers per hour and a time of 10 minutes. So we want to find our average speed. So to find our average speed, we need to take our total distance over our total time. That's what we need to do. So what a lot of people will do is they'll take out their calculator. They'll be like, oh, I got this. 2 plus 1.5 divided by 2. My answer is 1.75. It doesn't work. You can't do it because they're traveling for different times. You can't do it like that. You have to use this total distance over total time formula. So because we're given velocity and time, we can figure out how far they went in this first section. So if we use v equals d over t, rearrange that, and this is in minutes, this is in hours, but 30 minutes is half an hour. So we can plug that in. Half an hour, 2 kilometers per hour, we end up getting 1 kilometer. So they traveled 1 kilometer in this first part. This part over here, 10 minutes is 1/6 of an hour. So if I go 1/6 of an hour and I go 1.5 kilometers per hour, you can see how hours cancel out. That's why we end up with kilometers. And I can't do that one in my head, so I will calculate it. So I'll go 1/6. Put that in brackets, times 1.5, and I get 0.25. So in the second section, I traveled 0.25 kilometers. So now I'm ready to plug it into this. So my total distance is 1 kilometer and 0.25 kilometers. Direction doesn't matter. My total time, well, I go half an hour, and then I go 1/6 of an hour. So when I type all that in, I should be able to get my answer. So I go 1 times 0, oh, not times, 1 plus 0.25 on top. Put that in brackets, and then on the bottom, I go 1/2 plus 1/6. Put that 1/6 in its own brackets there, and I get 1.875. I have 2 sig digs, so my answer would be 1.9 kilometers per hour would be my average speed. So if I want to find my average velocity, well, the only thing that changes is direction, right? This direction I'm going north, so that one I'm going north for. This one I'm going south, so it'd be like that. So the only changes that I would make is this is plus 1 kilometer, and this is minus 0.25 kilometers. So if I go back into my calculator to turn this into an average velocity, I just push second enter. It'll plug in the last thing that goes in there. And then I go over the 0. If I push second delete there, that's my insert button, so I can insert a negative in there. And that's all that changes, right? Time is never negative because it's scalar. So my average velocity is going to be 1.1 kilometers per hour. It's positive, so that would indicate north. So 1.1 kilometers an hour north would be the correct answer. Okay, and then this last one here is what I consider a standard of excellence question. Mark and Steve both have to meet Terry in Kelowna, 1,200 kilometers away from meeting. Terry leaves half an hour before Mark and Steve and drives at a speed of 90 kilometers an hour. If Mark and Steve want to meet Terry in Kelowna at the same time, how fast do they have to drive? So let's draw out a little picture here. So this is Edmonton. This is Kelowna. I assume they start in Edmonton area. And they need to travel 1,200 kilometers to Kelowna. So Terry travels there, and it tells us that Terry travels at a speed of 90 kilometers an hour. Okay. Mark and Steve travel to Kelowna, and it doesn't, we're trying to find the speed. Okay, we know that both of them have a distance of 1,200 kilometers, because that's how far it is to Kelowna. So what that means is we have enough information to find out how long it took Terry to get there. So let's use V equals d over t. T equals d over v, like that. My distance is 1,200 kilometers. My v is 90 kilometers per hour. So if I do that, 1,200 divided by 90, I get 13.3 repeated. So that's how many hours it took them. So it says that Mark and Steve want to meet Terry and Kelowna at the same time, but Terry leaves half an hour before them. So if Terry leaves half an hour before them, what do we do to this? Well, Mark and Steve have less time, so we need to subtract half an hour from them, right? And when we get our answer, they should be driving faster because they have less time to do it, right? So it'll end up being 2.83 repeated. So when we subtract half an hour from that, right, that's what we end up getting. And we know they still traveled the same amount of distance. So if we just go 1,200 kilometers divided by this 12.83 repeated hours, I just have to go 1,200 divided by that. And that's how fast they're going. So they ended up going 93.5, but we just have 2 sig digs. So it's going to be 94 kilometers per hour. And it's asking how fast do they have to go. So fast usually means scalar. It's like speed. They don't want to know direction. Okay, so that's more of a standard of excellence type question. So let's do a board question and just pause the video, try it on your own, and then I will go through it right now. So the first controlled power airplane flight was by Orville Wright on December 17, 1903. The Wright brothers' airplane called the Flyer flew 12.1 kilometers an hour, and it flew a distance of 37 meters. Calculate how long the Flyer was in the air. So 37 meters isn't a very long distance, and 12.1 kilometers an hour isn't a very fast speed. They don't match up, but I'm thinking it's probably in the air for a few seconds. So I'm going to switch this up to meters per second. So that's the first thing that I'm going to do is turn that into meters per second. So if I go 12.1 kilometers per 1 hour and kilometers into meters, 1,000 meters in 1 kilometer, and hours into seconds, 3,600 seconds in 1 hour. I can find out my answer in meters per second. 12.1 times 1,000 divided by 3,600. And I get that as my speed. So from there, it's just a v equals d over t question. Move the t up top, move the v down below. It went 37 meters, and it did it at our speed of 3.361 repeated. So if I type that into my calculator, we don't want to round that answer, 37 divided by this, we end up getting 11 seconds. Okay, let's do one more. Tice drives 100 meters north for 17 seconds. Before realizing he forgot his cuff link, he turns around, drives south for 120 meters for 26 seconds. What is his average speed? What is average velocity? Okay, so pause the video and try it on your own. Let's draw out what happens. Tice drives a distance of 100 meters in a time of 17 seconds. Then he drives a further distance south, 120 meters, for a time of 26 seconds. So we're going to use v equals d total over time total. And our first distance is 100 meters. Our second distance is 120 meters. It's just speed, so it doesn't matter direction. Our first time is 17 seconds. Our second time is 26 seconds. So that's it. So if we plug that into our calculator, we end up getting 100 plus 120 divided by 17 plus 26. So we get our average speed to 2 sig digs to be 5.1 meters per second. Okay. To turn this into average velocity, all we need to do is add direction. So this is positive 100, this is negative, because this is north, this is south. So this is positive, this is negative. So I can just go back into my calculator, push second enter. I'll type in the last thing that was in there. And the only thing I need to change is I need to make this 120, negative. And that's our answer, is we get negative 0.47 meters per second, and we have to put south. Okay. If you don't want to put the negative in there, you can also put 0.47 meters per second south. Both are correct. Either answer is fine. If you put the negative or don't put the negative, it doesn't matter to me. So this is your homework. This is displacement stuff. This is free body diagrams and net forces. Make sure to only do the ones that I assign. And then this is v equals d over t and average speed and average velocity. Standard of excellence. SOE is standard of excellence, so these ones are a little bit harder. Thanks for watching.